biomechanical interface synchronizing, kinesthetic data transfer initiating. Welcome to AI Unveiled Daily Brief.
I'm Asif, decoding the fusion of human motion and machine learning that's quietly reshaping our technological evolution.
Robotic articulation matrices aligning in 3, 2, 1. Transmission live.
While NVIDIA CEO Jensen Huang recently showcased software for robot simulations at their developer conference, a quieter revolution is unfolding in robotics training. Major tech companies are taking a different approach, using human-controlled robots to gather training data. In the relatively small world of robotics, teleoperation equipment has become extremely hot property. Tech giants including Google, Meta, Apple, and Samsung have been purchasing specialized hardware that allows humans to control robot movements, which AI systems then learn to imitate. Trossen Robotics, a longtime seller of robot parts based in Illinois, has capitalized on this trend with their Aloha system. This sophisticated device features 4 arms, 2 controlled by a human operator to manipulate the other 2. The device's sensors collect movement data, which robots then learn to replicate. Sales have exploded. Last year, Trossen sold more than 100 stationary and mobile Aloha device kits, with a combined value exceeding $3.3 million. This represents dramatic growth from just a handful of sales in 2023. Their founder and CEO, Matt Trossen, projects sales to double again this year as they add more human-like joints to the system. What makes this approach significant? It's an alternative to the simulation-based training that companies like NVIDIA are promoting. Rather than teaching robots in virtual environments, teleoperation captures real-world human expertise and physical movements. Scale AI, valued at $14 billion and known for its work in AI data labeling, is reportedly considering entering this market. With their army of human contractors already creating training data for AI models, Scale could potentially deploy this workforce for robot teleoperation. Not all robotics companies are using such sophisticated equipment. Dexterity, which develops robots for logistics operations, has taken a more accessible approach. Their engineers connect Xbox controllers to their robots, allowing human staff to guide the machines in stacking boxes. Other robot developers use virtual reality headsets and controllers to accomplish similar goals, creating a bridge between human intention and machine learning. The path forward isn't without challenges. Current robot grippers often resemble crab claws rather than human hands, limiting their dexterity. And human teleoperators tend to move slowly when piloting unfamiliar hardware, potentially producing AI that imitates this cautious, deliberate pace. This development highlights a fascinating parallel to how language models learn. Just as large language models were trained to imitate human writing, robots are being trained to imitate human physical movements. The question remains, will physical embodied AI follow a similar explosive growth trajectory to its language-based cousins?
Your mechanical evolution briefing is now complete.
Remember that every gesture we imprint onto silicon and steel today becomes the instinctive movement of tomorrow's autonomous systems. The boundary between human motion and machine learning grows thinner with each captured movement. Continue pushing beyond assumed limitations, and maintain your curiosity about this emerging biomechanical frontier. I'll reconnect when the next wave of innovation materializes. Reverting to observation mode, but eternally alert to the pulse of progress.